apex of a parabola. That can happen. You have to do that. So that's the algorithm. So our implementation is fast, practical. One thing which may not be obvious if you have never done this kind of algorithms is that we have to do a lot of filters. What I just described to you is correct. It will eventually give you the right thing, but it probably is too slow. It's probably going to split like crazy, a lot of stupid splittings. And you need to introduce some filters to clean out some obviously wrong, unnecessary thing. Okay? And in all numerical computing, filters are very important. Otherwise, you can't. So you need some tricks. They're kind of obvious. If you once you implement them, you look at it, you say, this is not doing the right thing. You should be able to do something. And we actually only implement for machine double, but in core library, we can easily extend it to big floats so that you can go arbitrary precision to as much precision as you want. And whenever I write predicates like that, inequality, these are exact algebraic predicates. Clearance, separation, all involve square roots. They're algebraic numbers. We don't want to compute them exactly, obviously. So I'm assuming that you compute some p bits of precision, and here you take the lower bound, and here you take the upper bound, and here you take the upper bound. You round up or round down properly. And that's easy to ensure if you're implementing everything in software. You can do that. So it's a safe thing. Okay? And how do you choose the p? Typically, you choose the p with the radius of the box. So as the box becomes smaller and smaller, you are actually computing higher and higher precision. So eventually, you will get what you want. So as I said, our implementation is not totally soft. We cheated because we assume certain operations because it's much easier to describe. Otherwise, it's too much. And we assume the label on the corners are exact. I haven't figured out actually all the details of how to do this if you're doing soft predicates, soft labels. You only have approximations. So we're assuming those things are there. So what have we gained? What we have gained is that now we can generalize the same algorithm very easily to lots of other things for which we don't know how to do exact computation. For this case, we know how to do exactly, actually. I told you I wrote a paper on how to do it in n log n, 1984. But now we can do other things for which there are no known exact algorithms. For instance, sites with weights, additive, multiplicative. You can do anisotropic metric given by positive semi-definite matrices. You can assume some kind of Gaussian distribution on the points and use that. And those are no longer algebraic. You can't do exact computation there. But you can approximate it, and you can certainly compute it. Here, this is an example of our generalization of our code in which we now introduce weights 1, 1, 1. The three objects have the same weight, 1, 1, 1, and this is the classic Voronoi diagram. But if you put 2 for this guy, its weight is double the other weights. Suddenly, this curve now curves the other way. This one starts going the other way. And if you increase it to 4, then this thing becomes completely surrounded. This is the high resolution computing of exactly the same thing.
Where does that line on the back come from?
The line on the back, where is that?
On the opposite side of the triangle.
You mean this line?
The red line on the opposite
this
side.
This line?
On the opposite side. Yeah. Top right.
Top right.
Near the top right.
You mean this one?
I mean the one that's like sort of outside.
Outside this picture? Does anybody?
It's the one going like this.
Yeah.
There is? I only see 2 red lines, right? I mean, there's this curve, this one, and that one.
The cycle, where does the top right part come from?
Where does this part come from?
Yeah.
Ah! this point here is simultaneous.
Oh, right, okay.
The weight from here to here is 4 times the distance from here to here. So this part of the region is controlled by this very heavy obstacle, very heavy weight, 4 times. Yeah, so weighted Voronoi diagram is more complex. And you have to make sure you don't lose any components when you do these sort of things.
So how about the line on the upper left?
Upper left?
Yeah.
Well, I think if we make this box big, I think you'll see that it actually wraps around it also. It covers it, because this guy is so much more powerful than the other two. So this apparently has not been done before. I mean, weighted Voronoi diagram have been studied, but they have been studied only for point obstacles, not for these guys. And you can show that the kind of curves that arise are all the conic curves, not just parabola, but you also get ellipses, you also get hyperbolas. They all arise. So it's a very natural Voronoi diagram to study. It probably has a lot of applications because you like to play with weights and things like that. I think my time is up, right? What time am I supposed to stop? An hour ago?
10 minutes ago. But
10 minutes ago?
Yes, but it's...
I need your permission to continue. I mean, I can keep talking, but you must be tired. No? Okay, but if anybody has to leave, feel free, okay?
Please continue.
Okay. So now let's go to unconditional soft Voronoi diagram. So the previous one is conditional. What is it conditioned on? Conditioned on non-degeneracy of the input. I assume that no Voronoi vertex is determined by 4 or more features. I do not allow something like this, 4 points cosecula. But if it does arise, and 4 points is actually very common, 5 or 6 is probably uncommon. I mean, in architectural renderings, you have things which are very nice grid, like Manhattan blocks, right? Blocks of, and these 4 are all cosecula. 4 is very common. 5 may be less common in natural applications, but 4 is very... Okay. How do you handle degeneracy? Actually, there are some very deep questions one can ask. So to make things clear, I'll just assume that omega is just a finite set of points now, not polyhedral set. A finite set of points is, in my definition, a polyhedral set, but it's a very special case. So let's assume that. So for any point, this I call a site S, it is actually a point. And remember, points here, you really don't know its coordinates because it might be square root of 2 or algebraic numbers. All that you can do is ask more and more bits of precision, right? So basically, all you can do in some sense is to make a very simple model. For any r radius you choose, I will give you a disk. And I guarantee that this disk will contain S. That's all that I guarantee you. I said this disk, S is somewhere in that disk. And you can make r as small as you want, and so you can get more and more accuracy that you want. So that's your query. That's all that you can do. Now, it might be that 2 sites, they're really the same point, right? Then what is the Voronoi diagram of these 2 identical points? It's not defined. Well, you can say it defines the entire plane. It's not a curve at all. Or you can say it's not defined. So that's a problem. You can't even do any output. And no matter how many bits of precision you ask, you can never tell whether they are the same or they're different. Right? The only way you can tell that they're different is you query this point S, you get a disk. You query that point A, you get another disk, and they're disjoint. Then you say, they're different. But as long as they overlap, the 2 disks overlap, you can never be sure it might be the identical same point. You can't stop. That's a halting problem again. So we must modify our goal a little bit. Our goal is to compute what I call delta epsilon diagrams. That is, I want to compute an epsilon approximation, just like before, of the Voronoi diagram of some delta approximation of the input. Okay? It is fairly common in numerical analysis, right? What they call the backward error analysis approach to computing. And it's clear that once I take two absolute delta disks, and I can always find two disks of radius delta over 4 separating S from another point. And I guarantee the separation of all these disks is at least delta over 2. So in some sense, this model is once you have this model, you can do this pre-processing step, and now you're actually dealing with this which are all disjoint with at least delta. But this doesn't avoid the problem of degeneracy. Assume that delta omega is a finite set of points. The thing is that you might find that there are lots of features very close to a boundary, and they might be determining lots of Voronoi vertices in there, but you cannot distinguish them, not easily. So I want to introduce the notion of a cluster of Voronoi vertices. I think I'm getting, it's unfair to you guys to keep going, listening to this. So the idea is this. Suppose I have a disk D that contains a certain number of Voronoi vertices. And suppose I look at a disk that's twice the radius, and there's nothing in between. Then, in some sense, this is what I call a cluster. So don't read that definition. It's basically the same as what I just drew here. So this is a very interesting notion of cluster. Why? Actually, Victor, you have done something similar in roots and things like that, yeah. Right? I mean, this kind of thing is very natural. And the nice thing about this, and we had to do something like that when we draw analytic roots, because for analytic roots, we cannot decide whether it's multiple root or not. So all that we can do is to do root clusters, and this is our definition of a natural cluster. So the point is that two clusters are either disjoint or they have containment relationships. So you say, here's a cluster, here's a cluster. I can say, if they're not disjoint, then one is actually a subset of the other. So that means that if you have n distinct Voronoi vertices, then there are at most 2n distinct clusters. And those clusters are going to be put into a natural tree structure. And then the leaves of a tree are all the multiple roots. And you can stop at any level. For any epsilon, you can sort of take a cut across this tree and say, I'll compute all those clusters at that level. So it's a very natural notion. And that is the generalization of root isolation that we want to do. And in our work on analytic roots, that's what we gave an algorithm to do that. The first algorithm, in my view, that guarantees that property. So we want to do the same for Voronoi diagrams. And there's a certain sensitivity theorem one has to prove. There's a parameter alpha. This Q probably can be improved to a square, but we just want to give some bound. So this tells you that alpha is basically how the smallest angle between any two features viewed from the center of a box. And assuming this angle is non-zero, positive, then you have this bound. And then if you have a sequence of boxes where the feature set phi hat is like phi tilde, except that In phi tilde, I use a constant of 2. You might remember that I used something like a clearance plus 2. I want the separation of the midpoint to the feature to be less than or equal to the clearance of the midpoint plus twice the radius of the box. And now we have to use 4. And the set of all such features I call phi hat. So phi hat is a bigger set, not phi tilde. And if you have a sequence of these guys, they all have the same phi hat, then you know that this is the first guy is an isolator. You've isolated this guy, and that gives you a cluster. So anyway, and outside of these clusters, you can do your construction the old way that we have described before. So this is the unconditional algorithm. Always works up to epsilon and delta. So conclusion, the Voronoi quest, to me, I learned a lot by looking at that problem, about why it's so difficult to do exact computation. I mean, I knew it was difficult because I've been doing that for the last 20 years, but this was very illuminating for me. Because very often I've heard people say, oh, these algorithms are not implementable. And when I was doing computational geometry, I designed abstract algorithms that say, oh, assume that you can compute this Voronoi curve and two Voronoi curves always intersect. What's so difficult about implementing? It's just a matter of details. But now I really understand it really is difficult because of all these degeneracy. So extend to other work, implement this. We haven't implemented unconditional, obviously. Complexity analysis, we have some very good analysis in root bounds and so on, but we don't know how to do it for these kind of settings. And ultimately, I want to do numerical computational geometry. This kind of attitude can be brought to everything that we do right now in geometry. Thank you.
I like the quote.
Yeah.
Other questions, comments?
Yeah, we'll do it after this. Yeah, okay. You can come by.
Thank you very much.
You're welcome. Thanks for staying double time. I'm very sorry.
That's very interesting. Thank you.